Hello, my name is Kaylee Anakini, and I will be solving a combined spectral problem by identifying the unknown structure. I was assigned group 9. Since we have the molecular formula C10H12O, we can calculate the hydrogen deficiency index, or the degree of unsaturation. This calculation can help determine if there's any double bonds or aromatic rings. Since our formula doesn't contain any nitrogens or halogens, I decided to ignore it for the part of solving. So you have the degree of unsaturation 2 times the amount of carbon, which is 10, plus 2, subtracted by the amount of hydrogen, which is 12, all over 2, which equals 5. So we have 5 degrees of unsaturation. When we have 5 degrees of unsaturation, I would suspect that our molecule contains both a ring and a double bond. Moving on to the IR graph. An IR graph can help identify functional groups, especially functional groups that contain oxygen. Let's focus in around 1700. Around 1700, we see a peak that is consistent with a carbonyl. Since our formula only contains one oxygen, I'm focused on determining if there's either a ketone or aldehyde within our molecule. If we look right around 2600 to 2800, we can see 2 peaks that are consistent with an aldehyde. Since our degree of unsaturation also suggested that there is some aromatic rings, we can focus in around 3100 to 3300, as well as a peak in 1600. These peaks are consistent with aromatic or benzenes. Lastly, I would like to point out the peak around 2900. The peak around 2900 is consistent with the sp3 carbon-hydrogen, carbon-carbon bonding. The rest of the IR graph, especially from 1000 to 0, can be ignored. Typically, it's just fingerprinting. Next, let's move on to the CNMR. The CNMR has 7 unique carbons. I got that by just counting the spikes. This graph can be further broken down into 2 sections, 200 to 100 and 100 to 0. This represents the sp2 and the sp3. Focusing in on 190, this is consistent with our aldehyde. If the spike was after 200, it would be more clear that it was a ketone. But since it's less than 200, it's pretty clear that it's an aldehyde. Next, let's move on to the spikes between 120 and 160. This is in the realm of the aromatic rings. So we know that we for sure have an aromatic ring. Lastly, let's move on to the spikes between 20 and 40. These peaks are our sp3, our carbon-carbon, and our carbon-hydrogen bonds. Lastly, we move to the H&MR graph. This graph is important in identifying the location of the hydrogen within the unknown structure. Let's begin at 10 ppm. This is consistent with an aldehyde. It has one hydrogen and has one peak, meaning that it's a singlet. Therefore, it has no neighboring hydrogens. Seven to 8 ppm is consistent with our aromatic ring. Which has a total of 4 hydrogens. Given that there's typically 6 hydrogens, this graph tells us that this ring is di-substituted. To find out the orientation of the hydrogen on the benzene ring, we have to look into the splitting. Since both hydrogen groups split twice, they're both known as doublets. The only way to have 2 doublets on a benzene ring is if the di-substituted hydrogens are arranged directly across or symmetric. What I mean by this is you have your hydrogen ring. And the substituted hydrogens have to be symmetrical from each other so that they directly across. If your benzene ring, your substituted hydrogens were right next to each other, this would fall for a triplet or a singlet. It would not equal doublet bonding. Next, at 3 ppm, we have 1H. Although it's pretty unclear exactly how many peaks, I'm confident by saying there's a lot of peaks, which is most likely consistent with a neighboring hydrogen that has methyl groups. Last, let's move to 6H. I know I have 6 hydrogens and 2 spikes. So the neighboring will just have 1 hydrogen. With all of this information, we're ready to create our unknown structure. So we know that the aldehyde has no hydrogens. And typically, obviously, aldehydes are on the end of the structure. So I'm going to put the aldehyde right next to the benzene ring. The benzene ring has di-substituted hydrogens. So I'm making sure that they're symmetrical. Next, I have a carbon that just has 1 hydrogen. And is connected to 6 hydrogens, which is going to be a methyl group. 2 methyls. To make sure that all these graphs are correct, I can count the amount of carbons, which have 1, 2, 3, 4, 5, 6, 7. So I have 7 unique carbons, as well as a hydrogen that has, or an aldehyde group that has 0 hydrogen neighbors, a benzene that has di-substituted, and 2 methyl groups, so 6 more hydrogens, as well as a carbon with just 1 hydrogen. So this is a summary of my work and what we went over and my proposed structure. Thank you so much.